Okay, in this video, I'm going to do a few more examples illustrating using de Moivre's theorem for complex numbers. So we had previously done, I think it was 1 plus I to the fourth power. So I want to back up a little bit, and I want to do first 1 plus I squared, and then we'll do 1 plus I to the fourth power, and then we'll do 1 plus I to like the sixth power or eighth power, something like that. And I want to illustrate what's happening here. So previously I talked about how the complex numbers have a geometry to them. You could think of them as being arrows. Well, what do I mean by that? Well, let's get that going. So this is, say, 1, 2, 3 units. Let's say 4 units out, roughly. It's not spaced evenly, but whatever. It's close enough. 1, 2, 3, 4. So -4 in that direction. 1, 2, 3. Let's call that 4. So 4I, and then 1, 2, 3. Sure, -4I. It's not spaced evenly, but whatever. Good enough. So 1 plus I, we worked out the polar form already. 1 plus I, that was √2 times cosine of pi over 4, I believe it was. I guess I can just scroll up. It's right up here. Oh, we did 1 minus I. That's okay. We'll go with 1 plus I for the example that I want to do. That's better for this example, for the sequence of examples. Plus I sine of pi over 4. Okay, so if I square this, well, then I'm going to have to square the R value, right? And then double the theta values. So the square root of 2 squared, well, that's 2. Cosine, well, if I double the angle, that's pi over 2. Right? Again, this is, to make sure it's totally clear, this is √2 squared, and this is 2 times pi over 4. Okay? Plus I sine, I'm going to have room here, pi over 2. Okay. Now, cosine of pi over 2 is, of course, 0, right? So that term just falls away. And then sine of pi over 2, that's 1, right? So this is 2 times 0 plus I times 1, okay? Well, I times 1 is just I, and plus 0, well, that's just I still. So I'm going to have 2 times I. So this is 2I. Okay. I'm going to go back, and I didn't plot this point out. I kind of forgot to do that. 1 plus I would go over 1 up 1 unit. So that's right about here. Here's 1 plus I, right? Now 2I, that's just up 2 from the origin. So here's what I want you to think about. If we zoom in here, and I'll also make, well, that's fine. I zoom in here, and I get the straight line tool. So this is pi over 4. Oh, I do need to make the pen thinner if this is going to work. Come on. Yeah, pi over 4. I mean, I'd call it theta, but that's, you know what? I'm going to call it theta. This is theta, and this length is r. Well, this angle here to go up to 1 minus I squared, this is 2 theta. It's twice the angle. Now this is, I'm drawing this by hand. It's not perfect because the scale's off a bit, but this is 45 degrees. And then this is, of course, 90 degrees, right? And this distance is the square root of 2, and the square of that would be 2. So when you square a complex number, it rotates away from the positive x-axis, and it shifts further out from the origin. You square the distance, basically. So the larger the number, the more it moves out because you're squaring. So now if I want to do, well, what about cubed? What about 1 plus, to change my stylus back, I think, 1 plus I cubed. Well, I'm going to cube this R value. So this would be the square root of 2 cubed. Sorry, I'm getting some text messages. So the square root of 2 cubed, which will simplify a little bit. And then I need to triple the argument. So 3 times pi over 4. So root 2 cubed cosine of 3 times pi over 4. I guess I'll write it out long ways this time. I've got horizontal room, I might as well. Okay, so I could write this as the cube root of 8. That would work, but I could also write this as 2 root 2. Because I have root 2 times root 2 times root 2, right? I guess I might as well do this. And these two combine to make just 2. So 2 times root 2 is what I have. So this is cosine. And you're going to see that something convenient happens here. At least I'm expecting something convenient to happen. Okay. So 2 root 2 times, well, what's cosine of 3 pi over 4? Well, it's negative root 2 over 2, right? 3 pi over 4, right? Was negative root 2 over 2. And you might wonder, wait, hold on, why are we converting back to rectangular form? Well, I want to make a connection here. Sure, I could draw it using polar coordinates, but we've done that, and I want to make this a little more tangible. It connects to something you already know a little bit better. Plus I times, well, what's sine of 3 pi over 4? Well, oh, and I didn't change that here. Well, that's positive root 2 over 2. Okay, so when I distribute, I'm going to have, well, negative 2 root 2 over 2 plus I times 2 root 2 over 2. And I get some cancellation, these 2's and those 2's. What I have left over is negative 2 plus I times 2. Or if you want 2 times I, same thing, right? The root 2 times the root 2 is just 2. So there we go, negative 2 plus I times 2, or 2I if you want. So if I go here and plot that, oh, I hope I didn't make a mistake. I might have. Well, no, I guess not. Okay, so that's going to be like right here. Okay, and this angle, let me change my stylus size again. This angle here, I mean, it's getting a little cluttered. I'll try to make it work. This is 3 theta. And this is r cubed is the length. Okay, now if we do this again, what about 1 plus I to the 4th power? Okay, well, change back. So, oh, 4th power. Sorry. Okay, so this will be very similar to the one we did in the lecture earlier. Okay, so root 2 to the 4th power, that is 4 times. Well, these 4's are going to cancel. So I have cosine of pi, which is negative 1, and sine of pi, which is 0. So I get negative 4. Okay, so if I go up here, that's right here. And this angle, oh, I made a mistake here. I didn't complete that angle. So that angle was 3 theta. Now this angle, this is 4 theta. And that length here, I'm not going to label it because it'll just get maybe too cluttered. But this angle here, this is r to the 4th power. Yeah. So hopefully you can see how there's as you increase the exponent, the result rotates around, and it'll tend to do that. So if you keep doing this, it'll go around, and it will keep going out and make a big spiral. There's something that we're gonna do separately in a different video. This is the thing I said will be extra credit. What if you made like the square root of a complex number, or the cube root, or the 4th root? Well, what happens is, I'm trying to think, okay, what order does this go in? I think basically it does like this. Yeah, I could check some numerically, but I'm not going to do that right now. That'd be a separate video. They spiral in like that. So there's a starting point at the origin. There's a starting point at the origin. And then they spiral out after that. Okay. That's if the modulus is not 1. If the modulus is 1, we'll do some examples of that. Then the points just go around and around and around. So in fact, you know what? Let's do one of those right now. We'll take a complex number whose modulus is 1, and then we'll do that, and you'll see that it doesn't move away from the origin. The modulus remains 1 the whole time, and you'll see what I mean. So let's do this. Let's say we have different example. Oh, change my stylus tip. So let's say a different example. Let's say z equals, let's say, well, I don't want it to be too simple. Let's just say I. What happens with it, right? So this one, we don't even need polar coordinates for it. So I'm just illustrating that point. But you know what? We can do this. That's equal to 1 times cosine of pi over 2 plus I sine of pi over 2 in polar form. So let's keep that. This section is about the polar form, so we should be doing that. So if I say, oh, well, this is the r value. This is the argument, right? Modulus and argument. Well, z squared equals, well, 1 squared times cosine 2 times pi over 2 plus I sine 2 times pi over 2. So 1 squared is 1, right, times cosine of pi, which would be -1, right, plus I times sine of pi, which would be 0. So modulus is still 1. Okay, so if you plot this out, you're going to get a point that is 1 unit away from the origin. And if you do z cubed, well, this will be going back to the original argument and modulus, right? Oh, that's convenient. I didn't know it did parallelograms, the auto draw feature. So this will be 1 cubed times cosine of 3 times pi over 2 plus I sine 3 times pi over 2. Well, that's going to be 1, right, times cosine 3 pi over 2 plus I sine 3 pi over 2. So the modulus of z cubed is still 1. The modulus doesn't change when you, basically, if you multiply, if you multiply two complex numbers in polar form, you end up multiplying the two moduli together. Well, if you take one complex number with modulus 1 and another complex number with modulus 1 and you multiply them, the result has modulus 1. So if you plot these, they'll just go around in circles. So I'll do an example of that real quick. This video is getting kind of long, but we can finish that up. So let's say this, the snap 2 method. Yep, okay, there we go. So let's say this is 1, I, -1, -I. 1, I, -1, -I. Okay, so z was right here. Okay, this is z. z squared, if you put that back in rectangular form, or if you use polar form, you know, whatever, it's right there. Z cubed is right here. Z to the fourth is right here. And then z to the fifth would be the same place that this one is. Z to the sixth would be the same place this one is. Z to the seventh, same place as that one, and z to the eighth, same place as that one. It just spirals around in a circle. Okay? And if you started with one that was, say, like right, you know, let's do this. 1 second. I'm going to use that auto circle tool, and we will see I guess we will call that close enough. If you take a point like this, let's call this W, and you square it, you're going to get like right here. And then next you're going to get like right here, and then like right here, and then like right here. And it goes out by an even angle amount every time, but the radius, I guess that one's going to fall like right there. Okay, cool. I'm doing this by hand, so it's not perfect, but you know, these the angle shift amounts are supposed to be equal, but I'm drawing it by hand, of course. Maybe it would be better if I did this. If W was like right here, then W squared would be over here. And then W cubed would be right here. W to the fourth would be right here. And then W to the fifth would be like right there. And then W to the sixth would be right here. So what W would do that? Well, this would be 1/2 plus I root 3 over 2 would do that. And the modulus would always be 1 as you raise it to higher and higher powers, and it would just go around the circle. So this video is plenty long, over 17 minutes now. So I'm going to stop it in just a second. If you would like to see this W worked out, kind of like this one, where I went through working, well, like both of these, where I went through working out the de Moivre's theorem application, then I can do that. Just send me an email. I don't mind doing it, but you know, I don't want to overload you with additional stuff. If if this is good enough, why make another video that no one watches? But if you'd like to see it, just send me an email.